In our optics we have two experiment. One is the neutron string. In neutron string we find the wavelength of sodium light using interference pattern that is created by the neutron string. So before going to the experiment, we'll have an idea how the sodium vapor lamp works. So this is a sodium vapor lamp. So these are the filament in the sodium vapor lamp, and this filament is maintained at a potential at negative voltage and there is also a cathode which is maintained at a potential of positive voltage. Now when you apply a power supply and you apply a voltage between these two terminal, let's say about 450 volt, and when the filament will be heated, then the electron will be generated by the method of thermionic emission. So electron will be ejected out from the filament. Initially this gas tube will be evacuated, means all the gas particle will be sucked out using a pump. So there will be no gas particle remaining in the tube, and deliberately we will put argon and neon gas in the gas tube. So now when the electrons will be ejected, they will have a kinetic energy, they will have an acceleration towards the positive terminals of the circuit. In the process, these electrons will collide with the argon and the neon gas particles. So this electron can collide with the argon, and this can collide with the neon as well. So when electron hits a argon or a neon, it will excite the argon atoms and the neon atoms. So that is why initially there will be a light pink orange color in the tube. So you can see there will be a light pink orange color. So if you remember, the color will be like, I'll try to show you what was the color. So the color will be like this. Let me just select the color. So actual color, it was almost so the color will be like this color, pink orange color. So this color is due to the collision of electron with the argon and neon gases, and the argon and neon will have a electronic structure on the energy diagram. Let's say it is E0 and E1. So when the electron hits an argon, electron will be excited to the excited state and it will relax back. So in the process, a photons will be emitted. Let's say that photon has a wavelength of lambda. This lambda belongs to the wavelength of this pink plus orange color. So this is the concept why initially if you turn on a sodium vapor lamp, you will see orange pinkish color. So now as gradually these electrons colliding with the argon and neon, it will excite them, as well as due to the heating of this filament, this argon and neon gas particles will carry heat towards different parts of the tube. And in this process, the solid sodium atom, which is initially at these locations, at these bits, or it can be randomly anywhere in the gas tube. So this heat will melt the sodium atom and it will vaporize. So now all the atmosphere in the tube will be dominated by the sodium atoms. Okay. So now electron will hit sodium, it will ionize the sodium atom, and secondary electron will be ejected. These electrons can further hit another sodium atom and another secondary electrons will be ejected, and this phenomena will goes on. So as soon as an electron hits a sodium atom will be at excited state. Now if we look at the energy diagram of sodium atom, we have ground state, let's say it is E0, we have first excited state E1, we have second excited state E2. Now if an electron is excited to E1 and it relax back to E0 ground state again, then it will emit a photon. Let's say it is lambda 2. And let's say if another electron which is of more sufficient energy, that is greater than E1, and it can reach up to E2, then it can relax back to ground state E0 as well. So in that process, photon will be emitted of wavelength lambda 1. So clearly, as the energy gap between E2 minus E0 and E1 minus E0, E2 minus E0 is greater than E1 minus E0. So the wavelength which is emitted from E2 to E0 transition, E2 to E0 transition, this wavelength lambda 1 will be less than lambda 2, because the energy gap is small here, so wavelength will be bigger here. So let me correct this one. So this will be lambda 2 will be greater than lambda 1. So this is your lambda 2. Let me correct all these things. So this is your lambda 2 and this is your lambda 1. So one wavelength is 5896 angstrom and another is 5890 angstrom. So we can take the average value 5893 angstrom or 589.3 nanometer. So this is the wavelength of sodium light. So this wavelength belongs in the yellow region. So yellow color of light will be emitted in this process. So once the sodium atom is accelerated, then the color in the tube will be yellow. So the tube will be yellow like this. Okay. So what I have said, I have just typed it in words. You can go through it. So the process of thermionic emission, the process through which current is generated, it is proportional to actual temperature square. So if you heat the filament at higher temperature, then more current will be generated. That means more electrons will be generated. So all these things I have just written here. You can go through it. So with this feeling, we can differentiate between a normal yellow light or a sodium vapor lamp. So as soon as you turn on sodium vapor lamp, there will be pinkish orange color, and slowly it will take some time to become yellow. So in our lab we have two experiments. One is the Newton's ring experiment and another is the diffraction grating. Using both of these two experiments, we can find the wavelength of sodium light. Let us first go through what is Newton's ring experiment, how is the setup looks like, what are the theories behind it. So before going to the Newton's ring experiment, you must have seen a pattern like this, ring-like pattern in the Newton's ring experiment. So we will try to explain why the patterns are ring and how to find the wavelength of sodium light in this case. So if you remember, if I ask you what do you mean by interference? So interference is nothing but when two or more waves having a constant path difference overlap in space, then alternate regions of darkness and brightness are produced. This phenomenon of light is known as the interference. So this is a wave property of light. So as you can see in Young's double slit experiment, if the rays are travel in different paths, then they will interfere with each other, and if they meet constructively, then their amplitude will be added, then we will have a bright spot. And if the amplitude cancel out like these regions, these dark regions, then the intensity will be minimum. So that is known as the destructive interference. So the interference pattern to be happen, two conditions must be satisfied. The light source must be coherent, means they emit light waves that are in phase, and they should also be monochromatic. The light source must be monochromatic, that is, they will emit a single wavelength. So in this case, if it is a red color, then we will have alternate regions of darkness, that is black and red, like that. If we will have a yellow color, then the regions will be black, yellow, like that. So this is a interference pattern. So I have just written down what is constructive and what is destructive interference. So in constructive interference, when the amplitude of two waves after interference is maximum, that is the amplitude is added up. Let's say if you have amplitude A and another amplitude A, then they will add up to 2A. Then the maximum intensity of light will be produced. Then that region is bright, and this region is called constructive interference pattern, this pattern. Now if we go to the destructive interference, like these regions are all black. So these are the regions where destructive interference patterns are formed. So when amplitude of waves vanishes, then intensity of light is minimum, and this forms a dark region in space. This is known as destructive interference. Now if you remember, I will just write down this path difference between two rays. For constructive interference, it was 2n into lambda by 2. And for dark, that is destructive, it was 2n plus 1 into lambda by 2. That is, it is even multiple of lambda by 2, and this is odd multiple of lambda by 2. So wherever the rays will interfere as an even multiple of lambda by 2, there will be path difference satisfied. Then those regions will be having constructive interference pattern like this. Okay, and those regions which will satisfy the condition of odd multiple of lambda by 2, like these regions, then they will have destructive interference pattern. So these are the basic concepts that we have learned in Young's double slit experiments in our optics classes in class 11. So now interference pattern in neutron string. What is the interference pattern? So those who have done this beautiful experiment, you must have come across this pattern. There are concentric regions of rings. As you go far away from the center, the diameter of the rings increases. So this is the diameter of first ring, this is second ring, this is third ring, and so on. So as you go away from the center, n increases, then your diameter also increases. So first we'll try to explain why these patterns are forming. First of all, how the interference patterns are forming like this. So this was a typical setup. We have a light source here, that is sodium light source. Then we have a convex lens. We have a semi-silvered glass plate. This semi-silvered glass plate can reflect and as well as it transmit light. So whenever light is falling from the convex lens, it will produce parallel ray as the light is in focus. So this light will reflected towards the plano convex lens. And from the plano convex lens, after these light rays are coming, it will be reflected from the top surface of the glass air film, and it will also be reflected back from the bottom surface of the glass air film. As you can see, between ray 1 and ray 2, there is a extra path difference here. They have not traveled in the same path. So that means certainly this ray 1 and ray 2, they will have a path difference. Now if this path difference is odd multiple of lambda by 2, then there will be a bright region. As you can go through, this condition is not same as it was like in the Young's double slit experiment. It is because in Young's double slit experiment it was 2n into lambda by 2. Now there is a extra lambda by 2 path difference because of there is a reflection from air to glass interface, that is rarer to denser medium. Because of this, there is a phase difference of pi is introduced, and phase difference of pi is equivalent to a path difference of lambda by 2. Okay, so extra path difference lambda by 2 will be introduced, so the condition will be like this. So now if ray 1 or ray 2 satisfy this condition, that is this path difference is odd multiple of lambda by 2, then they will form a bright spot on the screen. And if this ray 1 and ray 2 satisfy a condition such that their path difference is 2n into lambda by 2, then they will have a destructive interference, that is black spot. Now if you understand this, let us imagine this structure, this whole structure, this shape in the 3 dimension. If you imagine this in the 3 dimension, there is a sand and you press a metal sphere. What you will have? You will have a spherical cavity or hemispherical surface. So this shape is nothing but a hemispherical shape. So light ray at a particular position, let's say from this center to this height, this particular height, these rays are from. At same time, at same height, same interference pattern will be from here. So and they also satisfy either condition for bright or dark. So if this is dark, this will also be dark. So similarly, if you imagine a circle at same height from the center, then they will have the same path difference and they will produce a ring on the screen, because this is a plano convex lens and the shape of the air film shape is like this. So you can look at this picture. So from the center, as you go smaller height, so smaller ring will be from. As you go from to higher curvature, then higher order rings will form and their radius will be more. If you go to more height, as the thickness of this air film is increasing, then as you can see the radius is also increasing. So this is how the pattern is circle. Now have you closely looked, the center is a fuzzy dark region. So this is not just a dark spot but a fuzzy dark region. We'll also try to understand why the center is like that. First of all, at the center what is happening, we can look at this picture. Let's say this is ray 1 and this is ray 2. Both are reflected from the center, that is at n equal to 0 point. Then as you can see, both these ray has almost traveled equal path, so the path difference will be 0. So look at the condition in which case path difference will be 0. Is it bright or is it the dark? You put n equal to 0 in this equation and in this equation. You will find delta D is 0 in this case and delta bright is lambda by 2. So as the path difference is 0 here, the center must be dark as this satisfy this condition. So ideally on the screen we will have a dark spot here, but this is a fuzzy extended regions of dark. Why is it so? Let's say another ray, you look at this picture, is coming from here, another ray is coming from there. This is small path difference. So this small path difference is also will be close to 0. So ray whichever coming from here, here, here and here, all these regions will have a path difference that is close to 0. So they will interfere destructively and we will have a dark region in the screen. So that is why the center is dark. Now if you have gone through the manual, you will know that how we can find the wavelength. The formula was like this: lambda equal to dn square minus dm square divided by 4r n minus m. So this r is nothing but the radius of curvature of the plano convex lens. This was nothing but 200 centimeter in our case. So if you measure diameter of nth ring, let's say 20th ring, then you can get d20 square value. If you measure the diameter of 10th ring, then you can get d10 square values. So your n is 20 and m is 10. So you can put in the formula, you can calculate and you can find that the wavelength of sodium light easily. So let us just remove all these things. So this is all about a neutron's ring experiment. So there was another phenomena also by which we can find the wavelength of sodium light. What is that? That is a phenomenon of diffraction. So using diffraction of sodium light in plane transmission grating, we can find the wavelength of sodium light. How we can do that? So before going to that, we'll try to understand what is diffraction phenomena. So diffraction phenomena is nothing but the phenomena of bending of light around sharp edge of an obstacle. This is known as diffraction. Let's say if you have blade, that is razor blade. If you place two razor blade closely separately, there will be a small gap. This small gap acts as a single slit. So if light pass through this small gap, then it will be refracted at some particular angle. So that means light is bending. So this phenomena is known as diffraction phenomena. Now to find a wavelength using diffraction pattern, we must know the condition for the diffraction maximum. So that is A plus B sin theta equal to N lambda. Now what is A plus B? A plus B is grating element. Let's say we have a plane transmission grating. Plane transmission grating is nothing but there will be many parallel lines which are engraved using some particular technique that is called lithography. No need to know in detail. Let's say these markings are done with a UV high power laser. So there will be engraved in the glass plate, like you scratch the glass with a diamond tip. You can imagine in that fashion as well. So this grating element is nothing but distance between two scratch, that is the dimension of a single slit. These are parallel slits, many slits are there. So this dimension A plus B, this must be comparable to the dimension of wavelength. So if we are finding the diffraction pattern using visible light, then this dimension must be in the order of 352 nanometer to 700 nanometer roughly. Then only we can have a diffraction pattern using this grating. So in our case, we had 13,000 line per inch. So it was corrected. In manual it is mentioned 15,000 lines per inch, but the corrected value is 13,000 lines per inch. So we can find the dimension. So in 1 inch, that is at 2.54 centimeter, there are 13,000 lines. So what is the distance between two lines? That must be the total length divided by the number of lines. So that is what we have done. So this is nothing but the grating element. So this grating element, if you calculate, this is close to almost 2 micrometer, and we have visible light up to 0.7 micrometer for red. So this dimension is almost comparable to each other. So that is why we can have diffraction pattern using this kind of plane transmission grating. Now what we have done in the experiment, we had a collimator here, we had a sodium vapor lamp source here. Then from the grating, light will be coming out. If it is traveling in the straight line, then that is called the central maxima. We can put n equal to 0 here. Then from the center, if you go some smaller angle to both the sides, we will have spot same regions of brightness. These are called the first order diffraction pattern. And if you go to far away, then we will have second order diffraction pattern. You can easily see from the formula, for n equal to 1, your A plus V sin theta is equal to lambda. Okay. So lambda will be smaller as n is also smaller here. So depending on the wavelength of the light, your angle of diffraction, that is the angle from the central maxima to the first, let's just say theta 1. So this angle of diffraction depends on the lambda. Higher the lambda, higher will be the bending of light. Let's say if this bending is for, let's say this bending is for blue light, then for red light it will be more from the center. Okay. So like this, if we can measure the angle, this angle or this angle, like theta 1 or theta 2, that we have done in the experiment, how to do that, then we can find the angle for first order diffraction theta 1 and angle for second order diffraction theta 2. Then we can find the wavelength of sodium light. So these are the discussion from the diffraction of sodium light. So learn about what is called diffraction. What will be the diffraction pattern if I use, let's say, white light. So if you use white light, in every region there will be total Vapour pattern in every spot. Like first order maxima will have Vapour pattern here, blue will be closest and red will be outer. In the second order as well, blue, like that, Vapour pattern, red will be outer. So each order will have a set of colors because white light consists of all the colors. So depending on the wavelength, they will be separated at different angles. So we can separate the wavelength. So the practical use of a diffraction pattern or plane transmission grating, we can produce a monochromatic wavelengths. Let's say you have a white light and I want to extract some particular form of wavelength. Then you can place a detector here. Let's say we have a yellow light coming out, we'll place the detector here, or we'll have some receiver here so that we only catch yellow light, because we can bend the light depending on the wavelength of the light. So this type of device can be used in many spectral cameras where we need particular range of wavelength to produce our image. We can select our image depending on our practical use or application. So this is all about diffraction pattern. I hope you have understood it.